Alright, hi year 11s, this is Mr. Lim here again, and this is our second video in chromatography and gases. This is affinities to phases. So let's get started. Alright, so we're going to work out why things have different affinity to the different mobile and stationary phases. Alright, and from that information we can work out some more information about the components and how they move through those phases. Alright, so let's get started. Okay, so the affinity of substances to stationary or mobile phases is based on the intermolecular forces of attraction between the stationary phase and the components of mixtures. Okay, so we go all the way back to intermolecular forces that we've been learning about, right? Whether they will have dispersion forces, which all things have, or dipole-dipole, or hydrogen bonding. You need to kind of know all of that reasonably well, right? But the idea is that if they have matching polarities, polar and polar, or non-polar and non-polar, they will have strong affinities to each other. All right, so in this example here, I have this green component here again. This green component is because it's not the same color as the stationary phase, it doesn't have a high affinity to it, so it might go fly through here, stick to it only a short amount of time, and then move on to the next one, and then move through it fairly quickly. All right, but maybe this one here, the other one there might be more of the same polarity, all right? Whether it might be polar or it might have hydrogen bonding, all right? So this one here will stick on there much longer and will stay there for long periods of time before desorping again, and then absorbing to the next one, and then stay there for a long time, and then it will move through this mobile phase, it will move through the stationary phase much slower. All right, so the ones that are not matching will move through quickly, and the ones that are matching will move through slowly. All right, so we generally tend to classify stationary and mobile phases as polar or non-polar, but they can both be polar or both be non-polar. But then the degree of polarity, so we would say one is very polar or not very polar, would be identified as well. So for example, some stationary phases are very polar, and when you use a polar mobile phase like water, the polar mobile phase would be less polar than the stationary phase. All right, so effectively saying that, okay, you've got a very polar stationary phase, so this stationary, what am I talking about? This stationary phase is very polar. So that's these things here, very polar, right? But this mobile phase is also very polar, right? So if this mobile phase is also very polar, it's just not as polar as the stationary phase. They're going to move through it a little bit differently. All right, so this component here, which one do I want? I want this one. Come on, move, damn you. Oh, I've got another component here. All right, so here I have this, here I have this thing here, right? It will stick to the very polar stationary phase, right? And then stay there for much longer and then move on, because this stationary phases are much more polar than the mobile phase, all right? Alternatively, you can also have different levels of polarities and components, right? So maybe you've got a component which is not very polar, but a little bit polar only, and that little bit polar component, and it's not moving now, right? The lightly polar component will move through the very polar stationary phase faster than a more polar component would. And we'll go through that in a moment because that was a lot of words. All right, so the polar component would have a stronger affinity to the very polar stationary phase, right, compared to the polar mobile phase, which is what we were talking about. Let's move on. Right, so with this idea, we can identify information about substances based on their polarity and non-polarity and their movement through chromatograms, which is the columns there. All right, so here we have an example question where you've been given information that there is a polar mobile phase and a non-polar stationary phase. And so this information might be somewhere in the question. It might be quite a long question, and so you have to just find information about the mobile and the stationary phase, right? You have to read through it, make sure that you understand it, and then work out what's the mobile and stationary phase, all right? So we see here that the yellow component has moved through faster than the blue component. And remember, if it's moving faster through the stationary phase, does it have a high or low affinity to the stationary phase? It will have a low affinity to the stationary phase, right? Because it's moving very quickly through it. This yellow component has a low affinity to the stationary phase. If it has a low affinity to the stationary phase, it's not going to match the stationary phase, okay? The one that has a high affinity to the stationary phase, which will be this blue one, because it's moving slower, will match the stationary phase, right? This yellow one will match the mobile phase in this case, or be more like the mobile phase. So what you would then work out here is that the yellow one, where's my yellow? Where's my yellow? Okay, so the yellow one will have a high affinity to mobile phase and low affinity to stationary phase. And thus, because it has a high affinity to the mobile phase and low affinity to the stationary phase, and your mobile phase is polar and your stationary phase is non-polar, it is likely that the yellow component is polar, right? Because it has a high affinity to that polar mobile phase and low affinity to the stationary phase, which happens to be non-polar in this case. All right. Therefore, if we're also making the same conclusions about the blue one, therefore the blue one will have a high affinity to the stationary phase and a low affinity to the mobile phase, and therefore it will match the stationary phase, which means that it is probably non-polar. Okay, so that's the idea that you can talk about the polarity of the two substances. All right, here's another example. All right, we have three components here. So if we are saying that the polar mobile phase and very polar stationary phase, all right, we have to work out which one is the most polar to the least polar. Okay, so let's write over most to least polar. Let's rank these out. Okay, I'm gonna number these ones here, 1, 2, and 3. Okay, so let's have a think. The one that moved the furthest, which is number 1, has the lowest affinity to the stationary phase. Okay, so it has the lowest affinity to the stationary phase, and the stationary phase is very polar. Therefore, this one here has the lowest polarity. Polarity. Right, because if it had a higher affinity to the stationary phase, it would move slower, right? And so therefore, effectively, it has the least matching of the three. So it has the lowest polarity, so that's number 1, then followed by number 2. This number 3 has a high affinity to the stationary phase, high affinity to stat phase, and therefore has a high polarity because the stationary phase was very polar. All right, so the most polar is number 3, the least polar is number 1, and you'd be able to rank them based on their movement through the polar and the polar mobile phase and the very polar stationary phase. All right, so remember, the one, effectively what you might say is that the slowest one is the one that matches the stationary phase the most, right? Whatever that stationary phase is, okay? And then we can also find information about the components from the chromatogram or vice versa. So for example, here we have, right, two components, right? And these are like chromatophores, which are effectively like colored dyes and stuff. So this is the chemical that makes certain things colorful, Right, and so you'll see here that, it's got a benzene ring here, it's got a bromine here, but these two substances are effectively identical, except this one here has a second kind of ring structure here. All right, so from that information, we might say that they're both polar because they've both got this OH group, which means that it's going to have hydrogen bonding. Also, it has this bromine over here, which means it's going to have, it's just a polar molecule, right? But which one is more polar? This one over here is going to be less polar, more non-polar. Why? Because it has that extra ring structure there, which means it's going to have increased dispersion force. Increased dispersion force, which effectively means that it's going to be more non-polar. Right. This one here is going to be more polar because it's a smaller molecule and it's just going to have less dispersion forces. All right, so then we now look at the information that we are given about the chromatography, the stationary and the mobile phase. All right, and we can see here that they've got a non-polar mobile phase and a polar stationary phase. All right, so this one here, well, they're moving upwards this way. All right, so this one over here, this one would be the, well, it's the one that's moved the least. The blue one is moved the least, which means it has the high affinity to the stationary phase. And since the stationary phase is polar, this one is going to be more polar, right? Which means that this is substance number 1, right? That one over here, right? And I've color-coded that wrong, but really should be in blue. But anyway, right, so that one has a high affinity to the stationary phase because it hasn't moved much, which means it's more polar because we've got a polar stationary phase, and therefore it's the one on the left because that one is more polar. All right, then we've got the one on the right, which is the one on the red one here. All right, why am I doing that in blue? Doesn't matter. Right, which has a high affinity to mobile phase. And it doesn't really have a high affinity, it just has a higher affinity to the mobile phase compared to the other component. All right, this is all relative, right? So you don't say words like high, you really should say higher. Okay, so higher affinity to the mobile phase, right? Alternatively, you can say that this has a low affinity to the stationary phase. And really, I should be saying lower affinity to the stationary phase. All right, so since it has a lower affinity to the stationary phase, it's moved further, all right, which means that it is more non-polar or less polar. Both of those ideas are acceptable, okay, which means that it's number 2. All right, so that's the kind of thing that you're going to be asked to identify from these chromatograms, all right, and working out information about their components of those mixtures there. All right, that's it. Adios.